Okay, so today we're going to become detectives, but not the kind you see on TV. We're going to be rock detectives. We're going to learn how to look at any stone, anywhere, and read the incredible story that's locked inside. And our secret weapon for this? It's a science called petrology.
And that's really the big question, isn't it? Because every single rock, even a tiny pebble you find on the ground, isn't just a lump of matter. It's a history book. It's a document that tells a wild story of incredible heat, unbelievable pressure, and just millions, sometimes billions of years of time. We just have to learn how to read its language.
And that language, well, that's petrology. It's the science that gives us all the tools we need to understand a rock's entire life story, where it was born, how it was made, and everything it's been through. So let's jump right in. All right, so every good investigation starts with the evidence, and our first step is to know exactly what we're looking at. And that means really getting the difference between a rock and a mineral. You know, it's actually simpler than you might think. Just imagine a mineral is like a single perfect brick. It's got one specific chemical recipe. It's pure. Now a rock? The rock is the entire wall that's built from a whole bunch of those different mineral bricks, all cemented together. So to bring it back to our detective work, the minerals are the individual clues. They're the fingerprints, the fibers, the things we analyze. The rock itself? That's the whole crime scene. It's the location where the entire event took place. Once we've got that straight, we can open up our toolkit. In petrology, our main tools are the forces that literally forge a rock's identity. And the two clues that really crack the case every single time are pressure and temperature. These two things dictate a rock's entire story. Yeah, think of pressure and temperature as the rock's fingerprints. They're totally unique. By analyzing them, we can figure out if a rock was born deep inside the earth under crushing pressure and heat, or if it formed in much calmer conditions, somewhere near the surface. It's a lot like water, actually. We all get that water can be ice or liquid or steam, right? Well, minerals are kind of the same. If you change the heat and pressure, a mineral can totally transform its internal crystal structure, leaving behind these critical clues about what it went through. So how do we actually read these clues? Well, we've got this amazing tool called a phase diagram. But honestly, just think of it as a treasure map. For any mineral, this map tells us the exact pressure and temperature conditions where it's stable. So we just identify the minerals in our rock, check the map, and boom, we can piece together the exact environment where it formed. And get this is a perfect example. You've got quartz and you've got stishovite. What's absolutely mind-blowing is that they are chemically identical. Both are just SiO2, silicon dioxide. The only difference is the pressure. Quartz forms under normal, everyday pressure, but stishovite, it only forms under the insane, unbelievable pressure of something like a giant meteor slamming into the earth. Finding that mineral tells a story of absolute catastrophe. All right, enough theory. It's time to grab our tools and tackle a real-world case. Let's solve the mystery of one of the most famous rocks on Earth, granite. How does this stuff actually get made? So the story starts deep, deep underground with a big pool of molten magma. Now, as this hot soup starts to cool down, something really cool happens. The minerals don't all form at once. First, the ones that are stable at really high temperatures, like the dark-colored biotite, they crystallize out. Then, as it cools down even more, the lighter minerals like quartz start to form. And what you're left with is that beautiful, speckled mosaic of interlocking crystals that we all recognize as granite. So you see, each one of those different minerals is a fingerprint. It's a little time capsule that records the exact temperature of a single moment as that magma was cooling down. And by finding all the different minerals in the rock, scientists can piece together the entire cooling process step by step. It's amazing. Okay, so we've learned how to read these incredible stories, but you might be sitting there asking, so what? Why does this actually matter? Well, it turns out this detective work has some seriously important real-world consequences. Yeah, this is so much more than just a cool science. By studying the stories in ancient volcanic rocks, geologists can get way better at predicting how active volcanoes might behave, and that saves lives. By knowing which rocks form under specific conditions, we can find incredibly valuable mineral deposits, like copper. And honestly, our entire understanding of huge planetary processes, we're talking earthquakes, continental drift, it all relies heavily on the science of petrology. So after all this, you now have the basic toolkit. You are officially equipped to be a rock detective. You can now look at the world around you, at the very ground beneath your feet, with a totally new set of eyes.
So here's what I want you to do. The next time you're outside and you pick up a rock, don't just see a boring, lifeless stone. Look at it closely. Look at the different colors, the different crystals. And then ask it a question. What's your story? What secrets from our planet's incredible past are you holding for me to find?